Greetings and welcome back to video lecture series on computer architecture. My name is Dr. Prashant Bachanna. In this video, I will be learning logical microoperations and shift microoperations in the computer architecture. So first we'll see what are like logical microoperations. So logical microoperations are basically it will specify the operations for strings of bits which are stored in the registers. So there are different types of logical operations are there. That is like AND, OR, XOR and all. So logical microoperations are like bitwise operations. They work on the individual bits of the data. Let us say if there are 4 bits, the logical operations will be performed on the each bits. Let us say in this example we have taken the logical microoperation for XOR with the 2 registers R1 and R2 which are less. So this XOR operation is specified with this symbol, that is XOR symbol. Then so this here P R1 R2 which will indicates that the logical operations of the 2 registers. So in this the R1 register consists of the data 1010 and R2 consists of 1100. So if P is equals to 1, so if we write P colon R1 XOR R2, so which will indicate that if P equal to 1, then the OR operation then the OR operation of these two are done. So at the end, so if P is equals to 1, the OR operations will be done. Then the output will be, that is like 0 1 1. So this is the output of this operation. So if we write P R1 XOR R2, so with the condition that if P equal to 1, so the logical operations will be performed. So in the logical microoperation, the operations will be performed bitwise as shown in this. So this diagram, there are different types of logical microoperations, that is AND, OR, NAND, NOR, OR, and NOR and the NAND. So as all of you know, the basic operation of AND, that is it performs the multiplication operation, that is in this table it has been given A and B. So the AND operation is performed here. So in the AND operation, like if any one of the, if both inputs are 1, the output will be 1. In all other cases, the output will be 0. So similarly, in the OR operation, the addition operation is performed. That is as you can see here. So these are the basic 2 tables of AND, OR, NAND, and the NOR. So in the logical operations, we can list out some of the operations that is in this table here. So this is a logic function. This column represents the logic function, and here it is the symbol for the operation. Then the different types of symbols what we can use, like the British, German, and the other electronics instrumentation symbols here. So the buffer is represented with this. So the buffer, it consists of single input. So there will be 1 bit of input and 1 bit of output will be produced. So the same symbol is represented in the different cases. So this is a symbol for the inverter. So what is the function of inverter? If you give 0 input, the output will be 1 and vice versa. If the output is 1, if the input is 1, the output will be 0. So this is a symbol for 2 input AND gate. So this can also be represented like this, and this is a symbol for NAND, 2 input NAND gate. This is a symbol for 2 input OR gate. This is a symbol for 2 input NOR gate. This is a symbol for 2 input XOR gate, and this is a symbol for 2 bit XNOR gate. So these are the basic symbols of different gates that we have to remember. So here in the logical microoperations, let us say for the OR operation is represented with this symbol here, with this symbol, or we can write this also. So if I write A and B, so A or B. So for OR operations we can use this symbol, and For OR operations, this is a symbol, and for AND operations, all of you know. So for OR operations, we'll use this symbol, and for AND, we'll use the this symbol. This is for the AND. So so we can use different logical micro operations as you've seen in the previous table. So we can perform the different types of operations here. So that is, if P plus Q means, we can represent it as P like of R1 and R2 and R3 registers. So we'll see these operations for one by one now. So this table shows the different like 15 operations of 15 logical micro operations. So let us say in the first two columns, the two inputs are there, that is X and Y. The inputs are 0, 0, 0, 1, 1, 0, 100. That is 0, 1, 2, 3. So these are the list of 16 logical micro operations that can be performed on in the bitwise binary operations. So as we know some of the symbols of this, that is AND, OR, and XOR. So these are the different operations. We'll see one by one. So this symbol, this table shows the mnemonics for like the representation of different logical micro operations in the computer architecture. So this shows the Boolean operation, that is the 15 operations. So the first operation is like the clear operation. So if we the mnemonic is F arrow mark 0. So this will perform the clear logic operation. So for AND operation, we'll be writing A and B. So here A and B are the two inputs here. So this will do the AND operations, and this is the OR operation here. NAND operation, that is A. So then this operation will represent the transfer, that is, it will transfer the content of A to the function F. So then we can write A dash B also, that is, this will represent X bar Y. So X bar Y. So F4 is equal to this. So we can perform this list of, let us say, if you want to perform like transfer of B, then we can write this one. So B arrow marks towards the F. So if you want to perform XOR XOR operation, so we have to write A, F is equals to A XOR B. So then X plus Y bar is represented by this symbol, that is NOR operation can be performed. Then for OR operations, so for OR operations the symbol is A or B. So if you write A or B, so these are the mnemonics that we have to remember in the logical operations for 16 different micro operations. For XOR, for XNOR operation, this is like we have to write like A XOR B whole dash, that is XNOR operation, exactly the opposite of the NOR operation. Then if you then for the complement, this bar is using B dash. So this will do the complement of B. Let us say like if B is equals to if B is equals to 1. So complement operation in the sense, if you write F is equal to B dash means if B is if the B value is 0, 1, 0, 1, so B dash means the value will be like 1, 0, 1, 0. So and for the NAND operation, this is the symbol for the NAND mnemonic micro operation, and for this is for X bar A into B, that is A and B whole bar, that is NAND operation. So if you want to sell all the bits to the 1, then we will use this function. So these are the 15 micro operations which are performed, which can be performed, that is 15 different logical operations which can be performed on the like which can be performed bitwise in the logical micro operations in the computer architecture. And this figure shows the hardware implementation of 4x1 mux, that is to implement these micro operations. So whatever we have seen, these 15 micro operations, to implement these 15 micro operations, we use the basic gates like AND, OR, NOT, and the XOR. So here in this we can in this diagram we can see a 4:1 multiplex, that is mux. So which will have 4 inputs, that is 0, 1, 2, 3 are the 4 inputs. Then these two are the control bits, S0 and S1. So with the S0 and S1 are the inputs. We can say if the inputs are 0, 0, 0, 1, 1, 0, 1, 1, that is 0, 1, 2, 3. So we can perform if the inputs, if S0 and S1 are 0, 0, then it will perform, this circuit will perform the AND operation. Then if S0 and S1 are 0, 1, it will perform OR operation. So this gate will be selected. Then if S0 and S1 are 1, 0, then it will perform the XOR gate. So this gate will be selected and it will perform XOR operation. Then for complement operation, if both S0 and S1 are 1, 1, this circuit will perform the complement operation. So this is a circuit wherein we use like 4:1 mux. Usually this multiplexer is used to perform to select one if there are n number of inputs. So this multiplexer is used to select one input. So in each case, one of the gate will be selected and the output will be performed. So the logical microoperations can be used to manipulate the individual bits or like the portions of the word in a registers. And let us say consider the data in the register A and some data in the another register B. So it is that will be used to modify the contents of A. So we can, apart from these logical microoperations, we can use the different the registers to modify the contents of the other register. Let us say this is a selective set. If you want to set it, that A plus B is done. Then if you want to perform the complement operation, we use this one. Then for selective clear, we use this micro operation. We use this symbol, that is A dot B dash. Then to mask the bits of A and B, we'll use this micro operation. Then to clear, we use this micro operation. Then to insert, we can write like this, and for comparison, we do the XOR. We use XOR gate. So we will see these operations one by one. Let us say the selective set operation will set all the bits to the 1 in the register A, where there are corresponding registers values are all 1s. So let us say A, the before value is 1, and with the logical operand value is 1011, that is the value of the B. So after A plus B is done, this is the output. So this operation is called as selective set, that is the OR micro operation can be used for selective set of the bit of a register. So like this we can perform different micro operations like selective complement. So in this the value of A will be the selective complement operation complements the bits in a register A, and where all the values of B are 1. Let us say the value of A before is 1010, then if the value of B is 1100, if we do A XOR B operation, then the selective complement operation will be performed on the each bit. So we can say the XOR gate can be used for performing the selective complement operation. So like this we can perform one more operation, that is selective clear. So the selective clear operation clears to all the values of A to the 0. That is, let us say the value of A is 1100 and the value of B is 1010. So after this selective set operation, the output will be 0100. So the Boolean operation performed on the individual bits here is the A into B dash is the operation here. So if you do that, the selective clear operation will be performed. Then the mask operation can also be done with the help of these logical micro operations. That is, the mask operation is similar to the selective clear operation, except that the bits of A are cleared only where there are corresponding zeros in the B. Let us say the A value is 1100, then B value is 1010. So the operation is A equal to A and B. So the output will be 1000. So to mask a particular bit here, so this here the third bit is masked here. So like this, we can perform the different operations here. So apart from this, we can do the insert operation. That is, an insert operation is used to introduce the specific bit pattern into A register, leaving the other bit position unchanged here. So this is done as a mask operation to clear the desired position. So followed by an XOR operation to this. Let us say the value of A is original value is this one, that is 110001 1000 1011. If the desired value is this, that is 1011 and 1010A. So then, so this is the original value, and after we perform the mask operation, that is for this value. So here it is the mask values. This one, that is 00, all zeros here, 00, then ones, then all ones, ones. Then the value is, the intermediate value is A. Then, so these bits are added here. So these two bits are added, and at the end we'll get the desired value. So to perform, insert an operation, so a specific bit pattern, if you want to insert a specific bit pattern, that can also be performed. We can perform the clear operation also. So the clear operation, to perform the clear operation, it compares the words in the value A, and it produces all zeros results if the two numbers are equal. So if the two numbers are equal, then it will produce the value 0. So let us say the value of A is here 1100, and the value is 00. See, if both the bits are same, that is, the output will be 0. So you can see there. So the value of A and B, the LSB bit, the first LSB bit are 00, so the output is 0. So here also both the values are 0, the output is 0. So to clear operations, we use this operation. So in the logical, after the logical micro operations, we'll see the shift micro operations. That is, the shift micro operations are used used for serial transfer of data. So they are also used in the conjunction with the arithmetic, logic, and other data processing operations. So there are different kinds of shift operations are there. That is, shift left and shift right. So here, let us say it is having some value R1. R1 is having some value 1010. Then if I write SHL R1, then it will shift the value of R1 by 1. So the information transferred through the serial input determines the type of shift operations. So there are three types of shift operations. That is, logical shift operations, circular shift operations, and arithmetical shift operations. So the logical shift operations is one that transfers 0 through serial input. Then we will adopt the symbols SHL and SHL and SHR here. So these are some of the logical micro operations. Let us say, like here, SHL means this is logical left shift. Logical left shift. And if you write SSR means it is logical right shift. So this table shows the different shift operations. That is, here the symbols are given, and here is the description. So if you write SHLR, R towards arrow mark towards the R. So this SHL means logical left shift the content of R by 1. So that is, it will left shift the content of the register R by 1. Then SHRR means it will shift the content of register by right by 1. Then circular shift means it will circularly shift the content of the register R by 1. Then left by 1. Then CIRR means it will logically circular shift the value of R by right by 1. Then ASHL means arithmetic left shift operation. That is, it will arithmetically shift the content of R by 1 and the value will be stored in R. So if you write ASHR R towards this, the arrow mark towards R, so this will perform the arithmetic shift right. So whatever the content which is present in the R, so that will be arithmetic shift right by 1. So these are some of the logical shift operations. That is, logical left shift, right shift, circular shift, and arithmetical shift. So let us say logical shift right. So what it will do? So this will shift the content of R by 1. So this is the right shift operation here. Then left shift in the sense the logically the value will be shifted towards the left. So as shown in these figures. So as we have seen, there are three types of logical micro operation. That is like shift operation. That is logical shift, circular shift, and arithmetic shift. So we'll see these shift one by one. So in the logical shift operations, the serial input is here. The 0 is appended to the MSB bit here. Let us say this is a data here. Some data here 0 1. So here the 0 will be appended. So in the logical left shift, so the 0 will be added to the leftmost bit here. That is, and these are some of the notations. SHL means logical left shift. SHR means logical right shift. So example, if I write SHL R2 means the content of R2 will be shifted left by 1. And SHR means the content will be right shift the content of R3 by 1. So like this we can perform the different operations. Let us say like circular right circular shift. So in the right circular shift the content will be shifted towards the right as shown in this figure here. Then left shift means the content will be shifted towards the left here as shown in this figure. Let us say like if you write CR R2 means the content will be shifted by left by 1. Then in the arithmetic shift, it means for sign binary numbers, that is integers, we perform these arithmetic shifts, that is left shift and right shifts. Here also we have two types here for the sign numbers. So arithmetic right shift is denoted. So here the sign bit will be added at the MSB bit. So in the left shift, the sign bit 0 is added here, and at the MSB the bit will be taken. So like this, if there is an overflow bit, so before the shift, if the leftmost bit is like 1, then it is called as overflow bit. So that's also, these are the two types of operations we have seen in this video, that is logical micro operations and shift micro operations. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.